Okay, I hope Didi will add this 1 minute and 22 seconds. First of all, thank you to Dr. Brijesh and the organizing committee of CMAP. Content and
Hello.
so I don't want to which is not particularly simple given the enormity of the field, but it's a good topic to start because 2D is one of the most important materials or quantum condensed matter materials that we have today in global research plan. It's, as I'm going to show, 2D is now 22 years old. Okay. So there has been enormous progress in both fundamental side and application. What I'll try and do in the next 35-40 minutes is to give you an overall view of where 2D is. And I also understand there are plenty of students who may or may not have seen two-dimensional materials, but I'll try and reach out to everybody and try and see if there will be a take-home message which is connected to your work. Okay. So as far as what makes a material 2D is, as we understand, that it is essentially weak interlayer coupling, such as in graphite, and that is usually given because of its layered structure. Typically, the strength of the bonds, at least in vertical direction, in 2D is about 100 to 1,000 times weaker, which is why you can slip it out. 2D has been used as lubricant for decades. But now we can actually take out layers out and do science with it. As far as graphene is concerned, I think those who work in graphene already know that originally the electronic structure of graphene, which is at that point of time used to be called graphite, was done by Philip Wallace in Canada. Okay. The idea was at that point of time to simply calculate the electronic energy as a function of, in tight binding model, and it was found that at very low energies, the conduction band and valence band of graphene meet, forming a single point, which is called the Dirac point. And interestingly, close to a Dirac point, there is an energy which is directly proportional to the momentum. And this makes it an interesting material to start with, simply because now there is a difference in a type of energy versus momentum dispersion relation in convention to a standard Schrodinger's particle or free particle, where energy is proportional to square of the momentum, and hence it can have mass. The second one, that is graphene, because of its momentum, which is proportional, energy and momentum being proportional, electrons behave like photons, and that led to a lot of very interesting properties in graphene. Starting from the fact that graphene's electrons can bypass disorder because of its linear band structure, and that's why graphene devices became extremely high mobility. But as I'll show right at the end of my talk today, that this is the fact that graphene becomes equivalent to photon, or the light, that allows us to look at a whole new physics where graphene connects to other kind of physics, areas of physics like cosmology, like string theory, and so on and so forth. But let's see how it goes. So, as we all know, this was originally graphene's 2010 Nobel Prize went for exfoliating graphene in an exceptionally simple manner by pressing a scotch tape on a substrate and then making electrical contacts on it. This paper has been now cited nearly 70,000 times, which just came up in Science in 2004. Okay. Now, if you think this was the first when graphene was exfoliated, that was not the case. Actually, there were several groups in the world. This is Rodney Rove's group in Texas, and then also Philip Kim's group in Colombia at that time. They were all trying to exfoliate graphene single layer in various techniques. Some did really brute force technique. For example, this was in a low temperature AFM. They took a block of graphite and put it up on a AFM, and then tried to dip the whole thing in liquid helium and try to exfoliate. Didn't succeed to make single layer graphene, although they got very nice and thin layers, but it was eventually the scotch tape and substrate technique that won the Nobel Prize. Then eventually, at that same point of time, the chemists were trying to isolate graphene, and it was making nano scrolls by exfoliating graphene in molecules or large lithium atoms in graphite and then exfoliating them. But they didn't succeed to make electronic devices at that point of time. So today we all know what graphene is, and it's one of the most important materials. It has got fantastic electrical mobility. It has got high thermal conductivity, nearly 4,000 watt per meter per Kelvin. We have got surface area, which makes it very suitable for making batteries. Tensile strength, it is essentially, 100 times harder than steel of equivalent thickness. Then we have got nearly 98% transparency, makes it suitable for solar panel applications. And of course, because of its dense carbon atoms, sometimes it is also said that it can be used in gas barriers. Okay, so if I take a look at the way graphene field has progressed over the last, say, from 1947 onwards. This is a theoretical study on electronic properties. You have 1962, the first discovery of graphene as an individual layer, which you would be finding surprising. But they actually came from graphene oxide. That's when people started seeing that individual layers of graphene can be exfoliated or can be separated. But it was not for original graphene, but from graphene oxide. 1986, the first time the term graphene was coined. We then had 2004, the discovery of graphene. 2007, graphene was made flat. It was or suspended and removed from the surface substrate. 2008, we had first ink of graphene. People started understanding that if you have put large amount of graphene, you can get printable electronics, and that was an extremely important step. 2009, something tremendous happened. Actually, that's what. The 2009, we did two things. First, we've put graphene on copper foil, a CVD graphene. Turned out first time we can make very large area electronics. And immediately in the same year, we found that we can actually make graphene on transparent electrodes. So this large area graphene was essential if you want to do anything beyond conventional laboratory research with this material. Then 2010, they got the Nobel Prize. 2012, the graphene electronics became available. And then 2014, the batteries, graphene essentially came with the batteries, look high-quality anodes with utilizing its very large surface area. And then if you look at 2018, the era of Moire, essentially taking two-layer graphene and doing interesting physics with it, like superconductivity, ferromagnetism, and so on and so forth, got started. So that's my view of graphene's timeline, and there are, of course, others that have happened in between, and you can always change it. But anyway, but while graphene was going on, 2011, molybdenum disulfide came up in EPFL from Anders Chris's group. And exactly the same way, at that point of time, it was a joke that all quantum condensed matter physicists used to be moving around with a scotch tape in their pocket, and whenever there is some wall, you can pull it out and see if something new comes up. But anyway, so of course, molybdenum disulfide was a very different, although structurally very similar, but it was a different molecule. But because sulfur and chalcogen atoms, essentially you have the natural molybdenum disulfide was a trigonal prismatic structure, and it is a very nice semiconductor, particularly good semiconductor in the direct bandgap semiconductor at the monolayer form, which is very important because silicon is not. And as a result, some of the optical properties of molybdenum disulfide is far superior than that of silicon, including the very large absorption ability of light absorption by molybdenum disulfide. Even at the level of a single layer, the amount of light it can absorb is phenomenally large compared to the standard bulk silicon. But that's beyond optical absorption. Now, in case of molybdenum disulfide, we have, because of its semiconducting properties, at extremely small level, you have a serious application possibility in electronics. We have certain key areas or bottlenecks of conventional electronics can be sorted. One of the perfect example is short channel effect. Now take a look at, usually as you make more smaller and smaller electronic devices where the source and the drain are coming closer and closer, applying a source voltage usually decreases the barrier properties. That is, this is called drain-induced barrier lowering. And this kind of an effect becomes particularly strong in bulk semiconductors, which is where molybdenum disulfide and the semiconducting transition metal dichalcogenide systems become particularly of importance. And as a result, now there's a worldwide effort, particularly in major semiconducting companies like IMEC, like TSMC. They are trying to make graphene as a key, or making molybdenum disulfide as a key platform for electronics. I deliberately avoiding using the term post-silicon silicon electronics because that is unlikely to be the case. But certainly there are electronic applications that molybdenum disulfide and transition metal dichalcogenides will perform in conjunction or in a collaboration with silicon. So what do we have in 2D family today? Of course, graphene started in 2004. Then we have the dichalcogenides, where we have the semiconducting dichalcogenides, metal dichalcogenides, and then we also had layered semiconductors, which became topological semiconductors at some point of time. These are bismuth selenide and a class of compounds which have got a conducting surface state but a semiconducting bulk. I will not go into the detail. I will not have time for this. But there are many now are becoming more and more important. While 2004 graphene, 2011 TMDC, but if you take a look at recent developments in this field, you have got now oxides like BISCO, which is a superconductor. It's becoming one of the most important material which are used as a 2D layer for superconductivity. Then we have magnetic two-dimensional materials, chromium iodide, chromium bromide, and various other compounds in this class. And then, of course, you have the magazines, which are extremely important when it comes to applications in high conductivity, large surface area, and so on and so forth. Okay, good. So with this class, what we can do is that we found that we are still at the tip of the iceberg. Okay? In principle, as far as the calculation is concerned, there could be about 1,825 exfoliable compounds, which can, because there are the weak interlayer interaction, of which we probably have seen about 40 to 50. In addition to that, the polymorphism is one of the most important aspects. I mean, even if you consider one of this 1,825, you can see even in that there are enormous amount of physics and science that is there by taking one and giving it slight distortion in the lattices. For example, if I take a molybdenum disulfide, this is a naturally occurring trigonal prismatic structure, but then you make that one of the chalcogen layer move about a third of lattice constant, you get 1T, the octahedral structure, and it distorts, becomes a spin Hall insulator, but this one is a metallic phase. Now, if you ask why am I bothered by this? Simply because being metallic makes it a very interesting candidate for contact resistance engineering. If I want to use the transition metal dichalcogenide as a platform of electronics in the future, then first thing I need to do is to reduce the contact resistance, which will allow me to have very large current, very small specific contact resistance. For this, there are not very easy solutions. If you put metal on this kind of semiconductors, the Schottky barrier reduces the current. So if you have the same material, which is metallic, it reduces the Schottky barrier and you get very large current. So Manish Chawla's group, for example, at Rutgers at that time and now in Cambridge, they are working on contact resistance engineering by doping molybdenum disulfide so much that it actually goes from the 2H state to a 1T state. In addition to that, of course, there are the electrocatalytic properties of these metallic phase is extremely important. Large surface area, a lot of electrons to donate. As a result, it becomes a fantastic, highly efficient platform for hydrogen evolution and energy harvesting. We had done some work long time back. Essentially, we showed that by putting MOS2 on top of a surface. By straining it, you can stabilize these 1T phases. If that's not enough, then you have the huge range of band gap across two-dimensional materials, starting from boron nitride, which is 6 electron volt, to graphene's extremely small band gap makes it optically active over 15 orders of magnitude of energy. And that's staggering, given the fact that you are still talking about one class of material. Okay? So essentially, you have ultraviolet from microwave. Almost entirety of the electromagnetic spectrum can be covered by one class of this material. And that's why 2D optoelectronics, or optical properties, is one of the key areas of research today. If that's not enough, you now have ways of designing materials, and that's called atomic Lego, in which what you do is we look at one material and put it on top of the other and make a material which is essentially unstable. Well, let me see if I can play this video. Yes. For those who have not seen video in the past, this is how you make what you call van der Waals Lego. You take materials of different genre of 2D and then put on top of each other to achieve certain purpose of functionality or science, whatever you want to do with it. Okay? So this is, for example, a 4-layer structure of molybdenum disulfide, bilayer graphene, boron nitride, and graphene on top. Okay, there's a reason why I showed this because this structure eventually became a single photon detector. I'll come to that later. But what happens is that by taking different layers on top of each other, you can make structures that can serve certain specific purposes, devices. Okay, so basically this. You are trying to make material which doesn't exist in nature. Those of you who are Bengalis here can probably realize where these pictures come from. But in any case, sorry? You
can fly now.
Yes. Anyway, so we started this long time back, around 2013. This is light to electricity conversion. Just to give you an example, this we did long time back. Essentially, the idea is that by doing these heterostructures, you can exploit the best of two worlds. How? Say if you put MOS2, which is a semiconductor, and graphene together, and I shine light on it, the molybdenum disulfide essentially absorbs the light and sends the electron into graphene, and it continues to conduct electricity for a very long time. So this kind of became a paradigm shift as far as optoelectronics is concerned, because this electron and this hole, they don't recombine for many, many seconds, for example. Eventually this became, as I said, this structure which I showed you the cartoon of became a single photon detector, and the kind of single photon detectors that can resolve the number of photons in an optical pulse that is essential for application in quantum technologies, for example. Now there are many, many different kinds of applications of this. Van der Waals heterostructures. You have got light-matter interaction, thermoelectric devices, memory devices for brain-inspired memory. So there is a huge range of application that you can think of now with this class of material engineering on a chip, as I say. Okay, and then came 2018 and the Moire lattice starts coming in. And this is where this took the entire community by storm. And for example, why am I bothered? Because now by putting one layer of graphene on top, I can engineer the Brillouin zone. Effective Brillouin zone becomes smaller. The band starts repelling each other. And if I take the layer, the two graphene at angles of say 2 degrees,